Let us talk about this problem. We are given a string and this string contains 6 possible characters. These 6 possible characters are brackets, starting small bracket, closing small bracket, starting curly bracket, closing curly bracket, starting square bracket, closing square bracket. So there are only 6 possible characters in our input string and we need to find out whether this string contains balanced parenthesis or not. What do we mean by balanced parenthesis? The bracket which opened latest has to close first. Let's understand this by examples. For example, here, if you see this small bracket, it started first, then square bracket, then square bracket closed. So square bracket was opened later and it closed before. That is what opened latest and then closed first means. So this is fine. Then closing bracket, the small bracket closes here. So this is also fine, right? So this is balanced. For balancing, the number of opening brackets, the number of closing brackets should be same. If there are 3 small open brackets, then there should be 3 small closing brackets. Two square brackets opening, then 2 square bracket closing also have to be there. And this order should be followed, that the bracket that opened latest has to close first. Let's see this example. Here, the number of small brackets are 3, the numbers opening small brackets are 3, and the number of closing small brackets is 2. So that's why it's not balanced. If I add one more closing small bracket, then it would become balanced. Now, talking about this example also, there is a third example, which is slight variation of second. So what happened in this example, we have this small bracket, then we have this square bracket, and then we have small bracket closing. You can notice that the square bracket opened later, but the small bracket closed first, right, before the square bracket. That's why it's not balanced, right? This is balanced, but this is not balanced. Although the number of opening and closing brackets of different types are same, but still not balanced. Let's now see this example. This curly bracket started and closed, then small bracket started, then square bracket started, then small bracket started, then small bracket closed. So this is the latest open bracket and it closed here. Then square bracket was opened before it, so it has to close just after it, right? And then the small bracket matching, right? If I change any order here, any of the closing brackets order here, suppose I swap these two, right, then it would not be balanced, because the square bracket has to close second and because it was open second, right? So the latest one has to close first and the earlier one has to close latest. So this is balanced. This is an example of again one more unbalanced, because the number of opening brackets are 2 and number of closing brackets are 3. So now you have enough idea about the problem. Please pause this video and try to think of a solution yourself. As you must have guessed, this problem has clear last in first out property, right? The bracket that opened latest has to close first, right? That's why we are going to use a stack here. In fact, this is one of the classical problems and the most popular example application of a stack. If you try solving this problem even using naive method, and if you don't use stack, it's going to be super difficult. It's a problem which is inherently a stack problem. It's like, if you look at this problem, if you know stack data structure, it automatically comes to our mind that it's a stack problem. So we know how do we use stack here, right? Now please pause this video for a moment and think, how do you use stack? The idea that we are going to use here is, we are going to put open brackets in the stack, right? So when we see this bracket, we put it into the stack. When we see this again opening bracket, we put it into the stack. When we see a closing bracket, then what are we going to do? We are going to check it with the top of the stack. If top of the stack is a same closing opening bracket, right? In stack we are going to have only opening brackets, and when we are going to see a closing bracket, we are going to match it with the top of the stack. So if you see this example, initially we'll have a small bracket in the stack, then we'll have this square bracket. Then when we see this closing square bracket, we'll compare it with the top of the stack, right? That's the LIFO structure, right? That's what we need to check. So when you compare these two, they match, right? You are fine there. So you are going to remove this opening bracket from the stack, right? Because it has been matched, it has been processed. Now when you come to this small bracket, you are again going to match it with the top of the stack, and it's matching with the top of the stack, so you will remove it. And when the stack becomes empty and you have processed the whole string, you are done. You have balanced parenthesis. Let's see this example. What are we going to do here? We are going to put this opening bracket here, this opening bracket here, then this opening bracket here, As long as we are seeing opening brackets, we are going to keep pushing them into the stack. When we see this closing bracket, we are going to match it with the top, and top is matching. We are going to remove the top and we are fine. When we see this closing bracket, we are again going to see match it with the top and it's matching, so we are going to remove it. Now we have processed the whole string, but our stack contains one opening bracket, which clearly means there is an extra opening bracket. So which means the balance parentheses are not balanced. So we are going to return false in this case. Let's see this example. We push opening bracket into the stack, then we see this opening bracket, we push it into the stack. Now we see a closing bracket. And when you see a closing bracket, you compare it with the top of the stack, and top of the stack is not matching. Whenever top of the stack does not match, you are going to return false, because the latest opening bracket has to close first, right? The top of the stack has to match. So we are going to return false in this case. Let's now see this example. We are going to put opening curly bracket here, then we see a closing curly bracket, we compare two, we find a match, we remove the opening bracket from here. Now we see a small bracket, we push it into the stack. Then we see a square bracket, we push it into the stack. Then we see a small bracket, we push it into the stack. Then we see a closing small bracket, we find a match from the stack, we remove it. Now we see a square bracket, we again find a match, we remove it. Now we see a small bracket, we find a match, we remove it. So our stack has become empty and we process all the characters, we are done. We say true, return for true, we have found a balanced string. Let's now see the last example. So what is going to happen? We are going to push this, then we are going to push this, then we are going to process this, and the top of the stack is matching, so we are going to remove the top of the stack. Then we are going to process this, and top of the stack is again matching, and we remove the top. Now we have a closing bracket and the stack is empty. So in this case also we are going to return false. So you have enough idea. These examples cover almost all the test cases, right? You know the approach. Please pause this video and try to write down the complete code yourself. Before we talk about the complete solution, let's talk about this function matching that we are going to use in our complete solution. So I've written code in both Java and C++. This function simply takes two brackets, one is an opening bracket and one is a closing bracket, and tells if they are matching or not, right? Where are we going to use it? I think you must have guessed. We are going to pop an item from the stack, and this popped item must be an opening bracket. And the current bracket that we are processing, if it's a closing bracket, right, we are going to pop an item only when it's a closing bracket, right? So we have an opening bracket, we have a closing bracket. We want to check whether these two brackets are matching or not, right? For that purpose, we are going to call this function matching. So this function checks if the popped item from the stack is a small bracket and the current item is a small bracket also, then it returns true. Or the top popped item is a curly bracket and the current item is also a curly bracket, then also it returns true. And then the same thing for the square bracket. So we are going to use this utility function in the main implementation. You may try writing the code again yourself now and pause the video first. Here are Java and C++ implementations of the approach that we just talked about. So we are creating a stack first, right? In Java, there are two ways to create a stack. Either you use a stack class, which is a legacy class, and or you use array_deck class. Array_deck class is a modern class and better class, right? It doesn't cause extra overhead. If you're not working in a multi-threaded environment, you can simply use it and it's better than stack class. In C++, we simply create a stack, right? And after that, we traverse through all the characters of the string. I've used for each loop in C++. We can't use for each loop in Java for strings. We either have to use to_char array function or convert a string to an array, or we can use a legacy loop where we use indexing. So I've used this loop in Java to traverse through all the characters in string, in the given string. We get the current character as variable x, right? We already have the variable x here. And if it's an opening bracket, right, this bracket or this bracket or this bracket, we push it into the stack. This is a simple learn for this example. In the first iteration, we see it's an opening bracket, we push it. It's an opening bracket, we push it. In the third iteration, we see a closing bracket. We come into the else part. And what we do is, we first check whether the stack is empty or not. See, what happens is, suppose your string contains first closing bracket, right? Then you should be returning false, right? You should not be trying to pop out something when the stack is empty, right? We should return false in this case, right? This handles this case or handles other cases also, like if you have two opening brackets and then say three closing brackets. So these two will cause a pop, then the stack will become empty, and then you will have empty stack, and then you have to process this last character, right? So for that also we need this thing to be handled. So we handle that case here. And if a stack is not empty, then there is something at the top of the stack. We get the top of the stack using peek in Java and top in C++, and we compare it with the X. And we have already discussed the matching function. The matching function is going to check whether this bracket and this bracket, they are matching or not. If they are not matching, we immediately return false, right? We don't want to process anymore because the parentheses are not balanced. And if they are matching, we come to the else part and we pop this character from the string. And that's what happens here. When we see this character, the top is matching here, right? It's a small bracket and this is also a small bracket. So we pop this small bracket from the string and we from the stack, and we get this bracket. Now we see a closing bracket, we again pop this opening bracket and our stack becomes empty. And at this point our stack is empty. After the fourth iteration we come here, right? And if the stack is empty, when you come here you return true, otherwise you return false, right? So we are simply returning whatever this expression returns. Why are we checking for empty stack here again? See, if I have this string, say if I have 3 opening brackets and 2 closing brackets, what will happen in this case? You will be pushing 3 opening brackets one by one to the stack. Then you will see a closing bracket, you will remove 1 opening bracket. Then you will see 1 more closing bracket, you will remove 1 more opening bracket from the stack. And at the end of this for loop, you will have an opening bracket in the stack, right? And it's not balanced because your stack is not empty. For such cases, we have this expression at the end. So this is how this solution works. Stack operations like push is empty and is matching is also constant, peek is also constant operation, pop is also constant. All these expressions are clearly constant. So the overall time complexity of this expression is big O of n. Why am I saying big O of n, not theta n? Because you might return in the middle, right? So it might be possible that you don't even traverse the whole string and in the middle you decide that it's not a balanced parenthesis, you return. So the time complexity is big O of n, and auxiliary space is also big O of n. In the worst case, you have all the opening brackets first and then you have all the closing brackets. So you are going to take n by 2 space for opening brackets. So it's theta n in the worst case, but I'm using big O of n that covers theta n and all the lower values as well. So big O of n time and big O of n auxiliary space, and this solution handles all the cases that we discussed in input-output examples.